Wall thickness transitions are another favorite. Pipelines are built with a constant outside diameter. They're not built with a constant internal diameter. So every time that the location changes from, say, a agricultural to a commercial area, the pipeline thickness changes. And that change is purely on the internal diameter. So that's where the tool is going to be riding and is going to be hit. The nicer pipeline companies will put tapers in, so it'll go like that, which is nice for the tool. Occasionally you'll get them so they go like that, step change. So you're hitting a step change of 8 millimeters at 4 meters per second. That will rip off heads, or potentially can rip off heads if they're not designed properly. This is actually the similar sized tool as you saw before, and it's actually ran in an oil pipeline. And the problem there is basically there's just wax in the pipeline. That collects on the tool, it stops the mobility of the sensors, it can cause severe damage to the tool. In gas pipelines you won't have wax, but you can have scale, which causes it to be a nasty environment to be in. Dents in the pipeline as well. We're expected to actually be able to go through dents. And you can see the pig there, okay? Luckily this wasn't an intelligent pig, this was a proving pig. And this was actually caused by an explosive device. Sabotaging pipelines is fairly common in certain parts of the world. They hadn't heard of a shape charge because that would have ripped the pipeline apart. Some pipeline companies, to save money, will also make the pipelines out of 2 diameters. So on an offshore platform, it'll be 14-inch at the top, going down to the seabed, and then it'll go to 42-inch, okay? And they want you to try and inspect those changes in diameter. The worst pipeline in terms of diameter changes I've heard about starts off as an 8-inch pipe, goes to 12, then goes to 16, and then goes to 20. Okay? You cannot design tools to run in those range of pipe diameters. Pipe diameter changes in, going from 46 to 48 is a lot easier than going from 8 to 10 because of the space available that you have. And here's another one which is a favorite offshore. It's called a Y. Basically it's joining 2 pipelines. One's coming in this way, one's coming in that way. Occasionally we get asked to, most of the time you're asked to pig this way or this way. Sometimes you get actually asked to be pigged into the Y. And the tool has to then try and make a decision which one of those 2 branches it's going to go up. That can be interesting. Okay then. So I've told you about the horrors of pipeline inspection, okay? Now let's talk about some of the sensors we currently use. Predominantly we're using Hall effect sensors. We're using Allegro or Honeywell sensors. They record the magnetic flux leakage. From them we infer the depth, the length, the width of the corrosion feature, and then we can calculate the failure pressure. The other thing we tend to use on all our tools is an inertial measurement unit for getting the positional information of the defect and also calculating the bending strain. It's one thing to actually be able to tell a customer that they have a 50% defect in their pipeline. However, if they go out there and dig and they can't find it, the confusion is the defect there or is the tool wrong? So we use basically military grade inertial mapping units on all our tools to give basically positional information within a meter or so. So, my wish list, okay? For the Hall effect sensors, I would love to have much more an increased density of Hall effect sensors in the head. Currently, in say an inch like that, we have 9 Hall effect sensors. If I could get up to 20 or 30 Hall effect sensors in there, I'd be able to predict the depth of the defect to a much higher degree of accuracy. With that, I'd also like to reduce the power that these Hall effect sensors take, so that the tool can run for longer, or we can potentially reuse batteries. For inertial measurement units, power is a big concern. On some of our tools, the inertial mapping unit takes 50% of our available power budget. And of course, I'd also like less noise. Going forward, this is getting into the really is part of the wish list. I would like sensors which would be able to tell me the magnetic properties of the steel. because a 10-inch pipeline in Alberta is made from a totally different mill than a 10-inch pipeline in Italy. So if I can tell the magnetic properties, I can correct for the different mill manufacturers and get increased sizing accuracy as well. And my final one is determining the mechanical properties of the steel. So this is telling me the depth, length, width information, but the other part of the failure calculation is to do with the yield and the ultimate tensile stress of the material. If I can get accurate measurements of those, then my failure pressure calculations become much more accurate. So that's basically it. So I'm willing to take questions if you'd like.